let's do an example converting a base 10 number into a float. So we'll continue with the same 9-bit representation where we have a sign bit in front, 3 exponent bits, and 5 fractional bits. I'm going to do the number -13. So it being negative, I know the sign bit is 0. I know I'm expecting 3 exponent bits and 5 fractional bits. So that's my goal, is to fill that in. I've got the negative bit first already. So the first thing to do is convert this into base 2 value. So this is, remember, floats are sign magnitude, so I don't do a 2's complement conversion. Instead, I just take the number 13 and convert that into bits. And that's going to be, let's see, an 8 plus a 4 and a 1. So 1, 1, 0, 1. 8 plus 4 is 12, plus 1 is 13. Yeah. So now I have two choices. If this was a denormalized number, it needs to be in the form 0 point something, like 0.1101 0 times 2 to the -2. Because for our representation, the bias value is 2 to the k minus 1 minus 1, which worked out to be 3 for this representation, where k was the number of exponent bits. And so, since for a denormalized number, the exponent is always 1 minus the bias, or -2. But this number does not equal 1101. If I do 2 to the -2, I would end up with 0.001101. And so it gets smaller. So I can actually rule out the possibility that this is a denormalized number. There's just no way to make it work of 0 point something times 2 to the -2. So instead, scratch that, and we'll try it as a normalized number. Now, a normalized number always has to start with 1 point. So in this case, it really has to be 1.101, and then I'll pad it with a couple extra zeros. And it's going to be that times 2 to the something. And since I shifted the point up here, there's one at the end, it was 101.0, I basically shifted it 3 points to the left. And so to get this number back into its original form, I would need to shift it 3 places to the right. So in its normalized number form, it would be 1.10100 times 2 to the 3rd. And so I've converted it into the form that a float would actually use as its internal representation. So now all I have to do is pick out those pieces and work out the bits that correspond to these values that I've got. So for the fractional part, I've actually already done it. All right, we've got it in this form. It's a normalized number, so it has an implicit 1 point. So I have to write the explicit bits, 10100. So I'm going to copy those and paste those into place for my answer here. So now I just need to work out what the exponent is. Well, the exponent value was equal to 3. And the value is always the value of the bits minus the bias. And so whatever our bits were minus the bias of 3 gave us 3, which means that our bits, exponent bits value, must have been 6. 6 minus 3 is 3. And so our bits, 6 in base 2 is written as 110. And so that's my exponent value, 110. We could work that in reverse, and we just go through the same steps in reverse for the, so let me just delete all this stuff and do that in reverse. So it's negative, so I have the 1 at the beginning in the sign bit. The exponent bits are 110, which is the value of 6. Subtract off the bias, and I get an exponent value of 3. For the fractional bits, this is a normalized number, so I put a 1 point in front, 1.10100. To convert, the bits were just 10100, but the fractional value is 1.10100. We add that implicit 1 point to get the explicit fractional value. So that's 1, and I need to convert what's after the point into base 10. 10100, that's 16 plus 4 is 20 out of 32, and I got that 32 because there were 5 places after the decimal, or after the point, and so 2 to the 5th is 32. So 1 and 20 30-seconds, and I'm going to convert that and write it as 52 30-seconds. So now my overall value is 52 30-seconds times 2 to the 3rd, which is 52 divided by 32 times 8, and that simplifies to 52 over 4, which is 13, and then don't forget to apply the sign bit, making this negative 13. So we see that it works going the other direction. Now let's try it with a value that actually does work as a denormalized number. Let's say 23 out of 128. So it's a positive number. Again, I'm just going to fill in placeholders for all the bits, except for the sign bit. So first I've got to convert this into binary. So 23, let's see, that's a 16. If you subtract 16 from that, you get 7. So this would be 16 plus 4 plus 2 plus 1. Again, to write that as a float, we need to kind of get that in the right form. It's either got to be 1.0111 times 2 to the something, if it was a denormalized number. And since I had to move that 4 places, that would have to be times 2 to the negative 4th. If I've done that right, let's see. Or so I was going to try times 2 to the 4th, not negative 4th. Wow, I'm getting ahead of myself. That's not even relevant yet. So that's just 23, but it's got to be 23 over 128. And so to do that, if we have a fraction of that form where the denominator is a power of 2, we've got the numerator written out as bits, and we just need to make sure it has the right number of bits. 128 is 2 to the 7th, so this should be 0 point and then 7 digits after it that work out to be 23. And so I need to put 2 leading zeros. That's the part I missed before. So 23 out of 128 is, again, if we were going the other direction, we would convert this into 23, count there were 7 digits, and put it over 128. So again, going back, if I wanted to write this as a normalized number, 1.0111 times 2 to the something, that something would have to be, let's see, how many places did we move it? 1, 2, 3. It would have to be times 2 to the negative 3. Well, if we carried that through to its conclusion, the exponent value is negative 3 for that as a normalized number. And so the exponent bits would have to be negative 3 plus the bias. The bias is 3, so we'd have negative 3 plus 3. The exponent bits would have to be 0, 0, 0. And 0, 0, 0 for the exponent bits represents a denormalized number. So this is not a normalized number. Right? It just didn't work out. I couldn't come up with a valid exponent that made it work when treating it as a normalized number. So instead, I'll treat it as a denormalized number. And to be a denormalized number, I have to have something times 2 to the 1 minus the bias, or 2 to the negative 2 for a bias of 3. Because denormalized numbers always have a fixed exponent of 1 minus the bias. So it needs to be x something times 2 to the negative 2, and it has to have a 0 point at the beginning of it. Well, this number, can in fact be represented as 0.10111 times 2 to the negative 2. And so it works as a denormalized numbers. The most common numbers we use in most applications are our normalized numbers. And so you really have to kind of find one in a very specific range, very close to 0 typically, to fit as a denormalized number. You could also take your representation and just figure out what the largest denormalized number is and then check to see if the number you're trying to convert is less than or equal to that, which would make it a denormalized number, or if it's greater than that, which would make it a normalized number, at least for positive numbers. So now that we have these, we can go and fill in the bits. So it was a denormalized number, which means the exponent was 0, 0, 0. And since we have it in this form of 0 point something times 2 to the negative 2, we can just take that something, and those 3 make up our fractional bits. And again, we could do it in reverse. It's a denormalized number, which I recognize because the exponent bits are all zeros, so the exponent value is 1 minus the bias, which is negative 2. Fractional bits, we take that, the fractional bits of 1, 0, 1, 1, 1, we convert that into a fractional value by applying a 0 point in front. And then to convert that to base 10, we take the value of the fractional part, 1, 0, 1, 1, 1, treat it as a whole number, which is 23, divide it by 2 to the 5th, because there were 5 places after the point. So we have 23 30-seconds, and for our overall value, we take 23 30-seconds, and we times it by 2 to the exponent value of -2, which is 23 over 32 times 1/4, which is 23 over 128, which was our original number, so that confirms that